Okay, good afternoon, good morning class. We are Design Team 6 and we're going to go over the full way to make a printed circuit board throughout the design. I'm Alex Walensky, I'm the webmaster.
I'm Derek Brower, I'm the presentation prep.
I'm Phil Jaworski, I'm the document prep.
I'm Junjun Liu, I'm a lab coordinator.
And my name is Matt Affelt, I'm the team manager.
A little bit of an intro that we're going to go over. First we're going to talk about the software flow, and this is basically from start to finish how you're going to actually create your design and layout inside of the software itself. We're going to go over routing and board layouts. This is going to include things like how you want to put things onto your board, the different layers, different components that are going into it, and then how to actually make your traces and routing. Then we're going to go over the components of assembly. We're going to go over different components you can be using on these printed circuit boards, how they work, and how to actually assemble them onto the board. And then we're going to go into some electrical considerations, things you want to either avoid or things that you want to change this way or that way depending on the performance of what components you want.
Alright, and so as Alex said, I'm going to be going over the software flow. There are a lot of actual software packages you can use to design your layout. You have Altera, Eagle, PCB Artist, Tina, the list goes on and on. They're all going to have different user interfaces and different little tools available to them, but the general flow of creating your schematic and your layout will be the same. It's also worth mentioning that you actually don't have to create a schematic to fabricate a PCB board. You just need the layout. But there are numerous advantages to creating a schematic. As you can see in these two pictures, this is the schematic, this is the layout, of course. With the schematic, you can generally look at and tell what's going on if you're an engineer, know what the circuit does, or if you're looking at it for a couple minutes, figure out what it does. But if you're looking at a layout, it's very tough to figure out what's going on. And granted, these aren't the same two circuits, and this one is more complex, but even with a simple layout, it's really hard to tell what is going on. So it makes it easier to share your design, tell people what your printed circuit board does. It also makes it easier for you to check your routing, make sure you have all the routing correct. And schematic editors actually have a lot of simulation tools available. So you can build your schematic, simulate it, make sure it works correctly, and then if it does, you move on. If not, it's really easy and really quick to change the schematic, whereas once you're in the layout, it's a lot harder and it's more time consuming. So it can save you a lot of time down the road. And then schematic creation is pretty simple. There are a bunch of libraries in schematic or editor software that will have your basic components and a lot of chips available. If the chips aren't in the libraries available, you can go on the internet and download libraries from different sites, like Texas Instruments will have a lot of libraries for their chips available. If those aren't available as well, you can create your own manually. For the schematic editor, all you really need is a symbol and the pins, the numbered, and the right number of pins for a chip. Draw the symbol, add the pins on, and wire it up. And once you have everything wired up, you have your sources added. You can do the ERC, which is the electrical rule check. Make sure you don't have like a voltage source tied to ground or something silly like that. And then you can simulate it, ensure proper functionality, and then you can export it to your layout. And a quick thing, like I mentioned earlier, if you don't actually have your chip or component in your library, you actually have to make the layout as well. So to do this, if you have to custom make a layout for a chip, this is an example right here, and this is an 8-pad chip. And so you're going to actually have to go online, look at the data sheet, and they'll give you the dimensions for the pad, the spacing between the pads, vertically and horizontally, and you have to actually draw that. So layout software is actually just like a CAD tool. It's just putting, you're actually drawing the footprint of all your chips, all your components, and then you're tracing them together. And then, of course, when you export the files, they'll take that data and actually fabricate your board. So once you have all of your footprints in for all your custom ones, and the ones that are in the library will be exported, they'll come in, and you'll have your outline of your PCB board, and all the components will be off to the side. You can place them, of course, however you like. We'll go into more floor plan considerations later. You route them together. Routing, of course, is just adding the traces, which connect the pins. And another thing worth mentioning is that you can do multiple layers. So this picture right here shows how layers can be used. Traces can go underneath each other because they'll be on different layers. So you can actually overlap traces, and that's very advantageous as well. This is another example of layers. This blue right here is all part of the ground plane. So that's a 2-layer board. And in 2-layer boards, you don't have a lot of layers to work with, obviously. So you're going to have your ground plane, you have a lot of components stuck in it, and that's not very good for performance. So with a 4-layer or 6-layer board, you can actually dedicate almost an entire layer to your ground plane. And then after you have everything routed, all your layers designed correctly, you can add labels. This is very important because when you get your PCB back from fabrication, you actually need to know where all the components go. It's very hard to just look at it and know which capacitor goes here, which battery capacitor goes here. So you can actually add labels that will actually print on the solder mask of the PCB board. After everything's labeled, you run the DRC. This is a design rule check. It makes sure that traces aren't overlapping, they're not too close together, so electric signals can't jump between them. And then after everything's working and functioning properly, you can send it off to fabrication. There are two ways to do this. Some software packages are actually linked directly to a website, and if that's the case, it's as simple as clicking an Order Now button on the layout software, and you can generally go through a wizard, and it will send it off, and it'll get fabricated. Some are more open, and you can actually generate Gerber files. These can be sent to multiple vendors. You can actually choose your vendor, maybe shop around a little bit, and then they will fabricate it for you. And with that, I'll pass it off to Phil.
I'm Phil Jaworski. I'm going to talk to you about routing and board layout. It starts on important terminology, different kind of layers in a PCB. The metal layers is the conductor that connects each component. The silk screen is the white writing on top, so from an overhead view you can see where all the connections are supposed to be made underneath. And the solder mask is the green plating around everything. Traces are the metal conductors. The width of each trace is referred to as its trace. The space is the space between each trace, and when you're designing, you want to follow a general trace space rule. For example, if your trace is 6 millimeters wide, you generally want to have the spacing to be 6 millimeters wide as well. Some important terminology. Some more. Pads are surface mounts that are drilled straight into the board. They're for connecting external power, ground, stuff like that. And vias are drilled metal plated holes. As you can see here are some examples. Stub via A drills all the way through, straight through the board, connecting another layer. V connects 2 layers inside with the straight through drill. A through connects the top to the bottom. Blind connects the top to one other layer, and a buried via connects 2 internal layers on the board. So when you're laying out your board, you want to lay out by importance of position. You want to line your components in a common sense approach. For example, here we have our user input outputs. We put those near the edge because we're going to be connecting to it. So it makes sense to do that. And same with our sensor I/O. For our microcontroller and our JTAG, those are going to be talking to one another, same with everything else. So they connect, put near each other. And you want everything to be space efficient. You want the smallest board possible. So as you can see, there's no space wasted here. So this is a good example of good layout. So the software we've been using is called PCB Artist, and so I'll talk a little bit about how you would go with routing in that. You want to place components inside a green PCB board here, which will eventually be your final board. On the left we have all the components we want to use. The yellow lines are connections that need to be made. They're also referred to as rubber bands. So when you start, as a general rule of thumb, you want to put your inputs on the left, outputs on the right, power and ground at the top. And here we started laying out our board with our IC in the center. So for this example, we'll use a 2-layer board. The whole bottom level is grounded. Here's our final layout. Inputs on the left, outputs on the right, our ICs in the middle, and components are surrounding it, which is a pretty solid design. So we begin making traces. You generally want to start with the power and the grounds at the top. Our power is connected to our IC, and our capacitors at the top. And here, this yellow hole drilled is a ground, which is grounding out all the capacitors on the bottom. So here's an example of a problem you might encounter when you are tracing. Say you want to connect the top of C2 of the node all the way to this R4. You couldn't because there's a ground in the way. But since we have the entire bottom level as a ground, we can put a ground to the left here, a ground to the right, ground out C4 and C5 and C3 on the right. We can make a long trace around our output to R4. Generally, you want to avoid using long traces because the longer the trace, the more impedance they'll have on the board. But in this case, for a 2-layer board in this circuit, it's probably the best design. Now I'll talk to you about grounding techniques. There's series on the top left there. It has a common impedance and difference of potential between each component. Parallel has lower potentials, has a little more complex wiring, but there's still a high impedance. Generally, the best one to use is a multi-point. Generally contains currents from going into the ground plane and reduces inductance on the entire system. So generally, when you're designing a board, the more grounds, the better. So power distribution, there's different kinds of schemes you can use. A single point has multiple user components. They have their own power and ground with a single reference voltage. Multi-point is put together in a daisy chain fashion. It has impedance coupling, which isn't necessarily a good thing. And there's a star distribution, which is similar to the single point, but there's a central reference voltage, and all the traces are equal lengths from the reference voltage. So when you're designing, which is the best one to use, depends on what you're going for. If you want the best power, you generally want to use single points, so all the current's going to be flowing in one direction. And if you want the best signal processing, you generally want to go with star distribution, because say if there's a delay in the system, since all the user components are equidistant from the reference voltage, all the delays will be experienced at the same time. So with that, I will pass it off to Nick.
So as Phil said, my name is Zhongchun. After talking about the floor planning, I will cover some types of components. So here's a DIP, stands for Dual Inline Package. It's an electronic device with a rectangular housing and two parallel rows of the electrical pins. It's commonly used as an integrated circuits. It can be either inserted in the sockets or through hole mounted on the surface of printed circuit boards. Another choice of IC is SOIC, which stands for the small outline integrated circuits. It is a surface mount type of the DIP. The difference is bending lead, thermal characteristics, and occupying area less than the equivalent of DIP. BGA stands for the ball grid array. It's a package made with pins in grid patterns. If BGA need to be soldered down, the pins are replaced by the balls of the solders stuck on the bottoms, and then placed on the PCB with cover pads in grid pattern which matches solder balls. So reduced lead, obviously its benefits. Also the miniature IC package with 100 pins. And another reduced lead chip is QFN, which stands for Quad Flat No Lead. It's a pad with a copper lead frame and a thermal pad. The advantage is low weight spin profile, near chip scale, and most importantly, the parameter pads is the PCB trays. And here's some through-hole and surface mount resistors. So after the component types, soldering techniques need to be considered. As everyone knows, soldering is a process of joining two metals using a solder rod. Surface mount and through-hole are two ways of hand soldering. Surface mount, as the name applies, the component is mounted on the surface of PCBs. So the pad is prefilled with solders. The component is mounted after them. So while heating up with the solder tips, the wooden stick is held down the component so that align with the pads. So on the other side, through-hole is much easier to do a soldering job. So the components placed through the holes or via of the PCBs, and then via will be filled with the solders either on the front or back side of the PCBs. So hand soldering is cheap, but it imposes the placement limits. So the component package needs to be, say, above 8 times 5 mils. Solder reflow is another technique. It's a latest technique. It allows precise surface mount soldering, which is a package below 8 times 5 mils. So here's a typical way of processing the solder reflow soldering. The solder paste is placed on the pads, and after visually check a sufficient amount of solders, the component is mounted on the pads. And then after each component is put on the PC boards, the entire board is loaded into the soldering oven and baked. After a certain amount of temperature, the solder pads melt, or so-called reflow, which makes the joints. So the solder reflow is much complex and expensive, but it allows very dense amount surface mount package. And then I'll pass it to Phil. So, Matt.
Hi, my name is Matt. I'll be talking a little bit about the electrical considerations when you're designing a PCB. So when you're designing a printed circuit board, here's an example. On the left-hand side, we have just two simple components. We'll call them A and B. And what's shown is the ground plane. When they communicate with each other, the ground plane has current flowing through it, and the current path is shown roughly by those dotted lines. As you can see, it's a very direct path, and it spreads out to find the path of least resistance to find the lowest impedance possible between the two chips. So that's one option, is to make it just solid plane and have very low impedance. Part of the problem is that then current, as you can see, takes up the entire ground plane. So if you have some section of sensitive components, there'll be a lot of noise underneath on the ground plane. So one option is to cut this little path here. What that does is it says that no current can flow through there since the impedance is roughly infinity. So as the current talks back and forth between components A and B, all of it's forced around this cutout, and it leaves that sensitive area untouched with that current. So it increases the impedance between A and B, which lowers the performance there, but it isolates your sensitive circuits, which helps increase that performance. So as you'll see in printed circuit board design, everything's kind of a trade-off. You give up performance somewhere to gain performance somewhere else. And so here we'll go a little bit more in depth with the ground plane and traces in the ground plane. So as Nick was talking about, the dip sockets go all the way through the board. So if you have a dip socket in a multi-layer board, you don't want all the pins to be grounded. And so you have to isolate those pins somehow. By letter C, you can see there's one option to just cut a big slot out of the ground plane. Now this isolates the top and bottom of the ground planes from each other. So if you have current on the top part of the ground plane that has to go to the bottom, it has to go all the way around that slot. So a much better option would be something more like D, where you cut individual holes for each of the pins, so you're still isolating to make sure they're not all grounded, but current can flow through there. So it greatly decreases the impedance in the ground plane. Now, if you have to make traces, which is something you shouldn't do in general, you don't want to make traces in the ground plane, you want to make sure that when you do, you don't greatly increase the impedance in the ground plane. So A cuts the board into two halves, left and right. So if any current has to flow from the left side of the board to the right side of the board, all of it's forced around A to the top and bottom. Now this is a very high impedance for your ground plane, which means it's going to greatly affect all of the components on the board. So a much better type of trace would be B, where you start at your point, you go up to the edge, all the way around, and then back to the other side of your point. Now this increases the impedance of your trace. It's really a much longer trace. But for that one trace has slightly larger impedance, you get much better performance across the entirety of the ground plane. Now it's also important to remember that a multi-layer board is essentially a giant capacitor. You have a bunch of conductive plates with a dielectric in between. Now, of course, they try to make that as strong as possible so that there's not a lot of capacitance between the layers, but it does exist. And so if you have very sensitive components to capacitance, such as the input pin of an op-amp, if you have capacitance on the input pin of an op-amp, it'll increase the, it'll destabilize the circuit, and it'll also increase the noise of the circuit. So you want to get rid of that capacitance. So one option is to cut out the ground plane under there. So the red layer is the top layer, the blue is the ground plane. So as you can see, this is our op-amp, and we've cut out the ground plane below the input pin of the op-amp. This isolates that pin so that there's a lot less stray capacitance on that node. Now again, it's another trade-off. You've increased the impedance of your ground plane, but you've greatly increased the performance of your op-amp circuit. Finally, the last thing we'll be talking about is antennas. Now at 100 megahertz or so, the wavelength is roughly 3 meters, and for an effective antenna, you need a quarter wavelength, which would be 75 centimeters. So it's pretty unrealistic that you're going to have a 75 centimeter component on your board. So you don't typically have to worry about your components being antennas. What you do have to worry about are attached cables. Cables are much longer, and they'll meet that requirement fairly easily, and they can act as antennas. And so if you have a layout such as in layout 1 over there on the left-hand side, where the cables are connected on either side of the board, any noise they pick up will be picked up on, if they're good cables, it'll be picked up on both wires, so you won't get a lot of noise in the signal per se, but you're grounded those wires when they get to the board. So if they pick up different amounts of noise, you'll have different voltages on either side of your board. So now you've induced a voltage across your board, and you have current flowing all the way through your ground plane, which means you've induced a lot of noise across the entirety of your board by your layout. So a much better option would be layout number 2, where you put all the cables on the same side, so that any voltage difference between connectors 1 and connectors 2 is directly shorted, and all of the current goes directly from one cable to the other cable without interfering with the rest of your circuit. So I'm going to pass it off to Alex to wrap it.
So in review of what we've gone over so far in our presentation, first we started talking about the software flow and the main importance of having to make a schematic before making your layout, because it's not necessarily needed, but it definitely helps you for going back and figuring out if things don't work, and for other people that don't know what your circuit does, they can follow it a lot easier. And we also went over the different layers in libraries, how to use them, how to import them from the internet if they're not existent, or to actually make a part. And we also talked about the fabrication, how you'd go about doing that if your software supports it or it doesn't. The next thing we talked about was the routing and the board layout. We talked about different layers, the ground layer versus the top layer, different layers, boards. We talked about traces and how you actually want to go about making traces to avoid certain conflicts. We talked about through holes versus vias, when you use one over the other. We talked about the importance of positioning for our actual parts, talking about how you'd want your inputs and outputs on left and right side of the board and towards the edge so you can easily use them, as well as having all of your powers and grounds centralized towards the top or bottom so they're easy to use and access. Then we talked about different grounding techniques, why you'd use one over the other and the most efficient, and different power distributions, if you wanted to get one for more power or signal, which one you'd use. Next we talked about components and assembly. Talked about multiple different types of components that you'd be soldering and how to solder them to your actual board and why you would use one over the other. I talked about the through-hole ones versus the surface mount ones, why some are easier, which ones are better, and how to go about weighing the options for better performance in that scenario. And then we also talked about electrical considerations. Some key ones we hit upon were straight capacitance, why you want to avoid that, and how to actually go about avoiding straight capacitance by cutting out. By ground plane traces, why you want to use certain cutouts in your ground plane to reduce the impedance across the entire ground plane and to improve performance of other components. And then we also talked about why antennas exist, why you want to avoid them, and to avoid the radiating EMI. And are there any questions?
All right, thanks.